In Unit 10, we're going to discuss circular motion. In Section 10.1, I'm going to concentrate on some of the concepts involved with objects undergoing circular motion. To review, the velocity of an object is the object's speed and its direction of motion. It is a vector quantity in which direction is important. The acceleration of an object is the rate of change in that object's velocity, not just its speed, its velocity. And so there are three ways for an object to accelerate. It can speed up, it can slow down, or it can change direction. Up until now, we've been focusing on speeding up and slowing down objects, but we have not discussed what happens if the speed is constant, but the direction changes. And that's what's going on if an object moves in a circular path. Its direction is changing, and so it must be accelerating even if it's moving with a constant speed. And the scenario in which an object moves in a circle at a constant speed will be referred to as uniform circular motion. That word uniform refers to the speed being constant. On this slide, I'm going to cover some of the important definitions that I'll be using throughout the unit. If an object is undergoing circular motion, its motion will have some radius, and the radius is obviously the distance from the center of the circle to a point on the outside of the circle. The radial direction is the direction that points along the radius of the circle. It points like that. And as the object moves around in the circle, that radial direction is going to rotate around the circle with it. If we pick a different point, we can define the direction towards the center of the circle as the centripetal direction. Centripetal means center seeking, and so centripetal always points inwards towards the center of the circle. The opposite of that is the centrifugal direction, or center fleeing, and that always points outwards away from the center. The other direction, besides the radial, is the tangential direction, and the tangential direction is always perpendicular to the radial direction. And we always have a 90-degree angle between the radial direction and the tangential direction. If an object is undergoing uniform circular motion, its velocity is always tangential to the circle. And if we have an object rotating clockwise, we can draw in some velocity vectors for 4 different points. These velocity vectors always point tangential to the circle. The acceleration is always going to point radially inward, aka centripetal. Okay, the acceleration for an object undergoing uniform circular motion will always be directed towards the center of the circle. And we have an equation, this will go on the equation sheet, that can relate the speed to the acceleration. And here we use an A with a subscript C to indicate that it is a centripetal acceleration that's equal to the object's speed squared divided by the radius of the circle that it's moving in. If an object's moving in a circle, it's accelerating. And if it's accelerating, there must be a net force acting on it, because net forces cause accelerations. And the net force must be directed towards the center of the circle. Objects always accelerate in the direction of the net force. And the net force has to be equal to ma, but the particular acceleration that we're looking at here is a centripetal acceleration, so that's why we use an A sub c. And we refer to this net force as a net centripetal force to remind ourselves that that net force is directed centripetally towards the center of the circle. The centripetal force is not an actual force, just the way that a net force is not an actual force. It must be provided by at least one force. Usually it'll be a combination of 2 or more forces acting in the radial direction. At least one of those forces has to act radially inward or in the centripetal direction. And if this condition's not met, then the motion will not be circular. It'll be some other kind of motion. We might have linear motion, or it might fly off into the air and become a projectile and move in a parabolic path. But if this condition's not met, the motion will not be circular. Billy is swinging a ball on a string around his head, and he wants to release the string so that the ball hits his little brother. Not very nice, Billy. Where in the motion of the ball should Billy release the string? So Billy needs to release the string at the point where the ball is moving towards his little brother. And that's going to be the point in where the circle is tangent to the direction towards his little brother. And it looks like that. So the string is going to be perpendicular to that red arrow at the point where Billy should release the string. The string provides an inward tension force that keeps the ball moving around in the circle, and when Billy releases that, it will stop moving in a circle. The condition for circular motion will no longer be met, and the ball will stop moving in a circle. It'll start moving towards the little brother's head. Sorry, little brother. It's very common to describe the motion of an object in circular motion as there being a centrifugal force. And anybody that's ever been in a car that makes a sharp turn has felt this force, or if you've ridden this ride that you see in the GIF. You feel like there's a force pushing outward away from the center of the circle. And we refer to this as a centrifugal force, but it's not good to it's really not good to call it a force. I prefer to call this the centrifugal effect because there's no actual force pushing outwards. It just feels like there's a force pushing outwards. There's no such thing as a centrifugal force. That effect is the result of the object, or if you are the object, in a non-inertial reference frame, which we've discussed before. Accelerating or rotating frames are non-inertial. And so we invent these descriptions called fictitious forces. It seems like there's a force pushing outward, but when in fact there's a force pushing inwards. There's always a force that has to be pushing inwards, but it feels as though there's a force pushing outwards, and we call that a centrifugal force. And here's why it happens. Imagine that you're riding in a car along with a soda sitting on the seat next to you while the car turns to the left. Well, the soda has inertia. It wants to continue moving in a straight line as much as possible, but the car itself is turning to the left. Well, if you would see from outside the car, the soda moving forward, but to somebody in the car, it seems as though the soda moves out away from the center of the circular path. And what causes it to move out? Well, there is no cause. It's just the object's inertia. It's the soda's inertia trying to have it move in a straight line. It's you that is actually turning. But from your perspective, it seems like there's something pushing outwards, and we call that sensation or the experience of seeing something move outwards. We call that the centrifugal force, but it should really be called the centrifugal effect. But we do have some very practical uses for the centrifugal effect. If you've got one of these handy kitchen appliances called a salad spinner in your house, you can see this in action. You could also see this in the spin cycle in a washing machine. What happens is in this case, the salad is moving in a circle, and you can see that there's a sort of mesh screen that prevents the salad from flying off. There's an inward centripetal force applied to the salad, but that does not get applied to the water. The water continues moving off tangentially, and that separates the water from the salad. There's also this handy device called a centrifuge, and centrifuges are used to separate a suspension, which is a mixture of usually some solid-ish particles and some liquid. And the centrifuge will increase the rate that the suspensions separate. And you can see in this GIF that there's some muddy water that gets separated, and all the dirt particles end up towards the bottom of the test tubes. The bottom of the test tubes ended up being the furthest from the center of the circle that they're moving in. And we can use centrifuges to separate suspensions, and we can also use them to train pilots and astronauts to experience very large accelerations. On this slide, I'm going to show you how to convert units of angular speed. Here we have an old phonograph record rotating at 33 1/3 RPMs. What is the angular velocity or angular speed in radians per second? So we can start out by taking the original measurement, 33 1/3. RPM stands for rotations per minute. Now I don't want units of rotations. I want units of radians, and there are 2 pi radians for every 1 rotation. I can cancel units of rotations. I don't want minutes in the denominator, so I'll multiply by minutes over seconds, and for every 1 minute, there are 60 seconds. Minutes cancels with minutes. I'm left with radians over seconds, and this works out to be 3.49 radians per second. Here we have a CD rotating at 22 radians per second, so we should recognize that 22 radians per second is the angular speed. We want to know how many rotations that it spins through in 10 seconds. So if I take that 22 radians per second, and if I multiply it by 10 seconds, this is 220 radians. That's the angle that it has spun through. But I don't want radians in my answer. I want to know rotations. So I'm going to eliminate radians, convert it to rotations, and every 1 rotation is 2 pi radians. And this gives you 35 rotations. So we can convert between radians and rotations, and rotations per minute and radians per second. And we use that in this example where we have a centrifuge, which I mentioned before, that's used to train astronauts that's spinning at a rate of 20 RPMs. So 20 RPMs is not going to be a useful unit. We're going to have to convert that into radians per second. And so we're going to multiply by 2 pi radians per 1 rotation. That cancels rotations. And then we'll multiply it by 1 minute per 60 seconds. And when you crunch the numbers, you'll end up with 2 pi over 3. You could turn this into a regular number, but I'm going to leave it as a multiple of pi, radians per second. And I can use that number to answer A. We want to know the linear speed. So what is V? Well, to find V once we have omega, we just have to multiply it by the radius, which is shown right here. That will be the radius of the circle that the astronaut moves in. When you crunch the numbers, you end up getting 39.8 meters per second. Now, in part B, we want to know how many g's of acceleration that the trainee will experience. So this is a centripetal acceleration that we need to calculate. Centripetal acceleration is speed squared divided by radius. I just determined the linear speed v. I know the radius r. And when you calculate this, you end up getting 83.4. That will be in units of meters per second squared. But it doesn't want to know the acceleration in meters per second squared. It wants to know it in g's. So we need to know that a g of acceleration is 10 meters per second squared. So that means that the acceleration experienced by the astronaut is going to be 8.34 g's, or 8.34 times the normal pull of gravity. And so what force is this astronaut going to be experiencing? Well, we can calculate the amount of force by multiplying the acceleration times the mass. Well, it says that the astronaut has a mass of 100, and I'll multiply the centripetal acceleration in meters per second squared. And we end up getting 8,340 newtons. And I would like to point out that this is much more than he normally weighs. He normally weighs 10 times 100 or 1,000 newtons. This is 8.34 times as heavy as he normally is. This is why we will frequently refer to forces in terms of g's, because no matter what that astronaut's mass was, they will be experiencing 8.34 times as much force as they're used to just sitting on a chair. Okay, this particular astronaut experiences 8,340, but anybody sitting in that chair would experience 8.34 times what they normally feel. So, what if we double the rate of rotation to now 40 RPMs? Well, I'm going to need a little bit of space, so I'm going to clear some so that I can reason this out. And I'm back. So if the rotation rate is doubled, the linear speed is going to increase as well, because the linear speed is directly proportional to angular speed. If you increase the angular speed, you will increase the linear speed. We are increasing the angular speed by a factor of 2, and so that is going to mean that the linear speed, v, is multiplied by a factor of 2. And when we look at the effect on the acceleration, we should note that the acceleration is not directly proportional to the speed. It's proportional to the speed squared. So when we take the linear speed and multiply that by 2, that will not double the acceleration. That is going to quadruple the acceleration. So the new centripetal acceleration is going to be 4 times the original, or now 3.3 G's, not grams, G's. So real important. Students will often forget the fact that the centripetal acceleration depends on speed squared. So doubling the angular speed has the effect of quadrupling the centripetal acceleration.